Have you ever tried to escape a heat wave by leaving the city? That temperature difference is not just a feeling. It is the heat island effect. City centers can be up to 8 degrees hotter than the surrounding areas, worsening air quality and increasing cooling demand. We usually blame traffic and facilities, but data centers are becoming another major contributor. With the AI boom, more computation means more heat. But here is the opportunity. Non-urgent AI workloads are flexible, and we can move them between locations to get a better environmental impact. The challenge is that every location is different. Wind, temperature, and humidity all matter. So we built CoolLoad, an AI system that finds the optimal split of workload across data centers to reduce heat impact while keeping the same computations running. To find the optimal split, we first model how each workload changes local temperature under current weather conditions. We solve a heat transfer equation that captures 3 effects: heat added by workload and sunlight, heat carried through streets and buildings by wind, and cooling from convection and radiation. Here, you can see a heat plume spreading from a data center across nearby city streets. To work with real data centers, we built a website where an operator can upload a building specification. Gemma extracts key information, the address, area, and building materials, and passes it into the physical heat model. The operator can set the base, non-reducible workload for each data center, then choose how much flexible workload should be distributed across the network. They can also select the number of simulation steps and press Run Simulation. Behind the scenes, a Bayesian optimization process searches for the best workload split. It uses an objective function based on the predicted temperature and weighting factors and estimates the split that minimizes heat. After each simulation, the orchestrator sends the predicted heat plume images to local data center agents. Each agent checks whether the plume geometry creates a local risk, for example, overheating. If a problem is detected, the orchestrator adjusts the weights in the objective function and runs the simulation again. This loop continues until all local agents approve the workload split. Here, you can see that the second data center rejects the proposed workload because of an overheating risk. The orchestrator responds by updating the objective weights and rerunning the simulation. After a few iterations, all data center agents accept the flexible load, with the heat impact balanced almost evenly across locations. One question remains: where does the flexible load estimate come from? We propose a simple method. Developer teams submit their code or job description to Gemma. After a few clarification questions, Gemma estimates how much power the job will require. We then aggregate these estimates across all teams to calculate the total flexible workload. For example, for a code submitted that does fine-tuning of a 27 billion model, Gemma estimates an additional load of 0.002 megawatts, which will be sent to the flexible load pool. This is CoolLoad. Thank you for your attention.